Alright, so this is study guide 1, review of organic chemistry 1, and we are going to work on more practice. So the first one, we need to draw a full structure of CH3CONH2. So that is CH3. So H is connected with this C, CH3. Then C double bond O and N H2. So H is here, and 2 electrons. So this is the full structure. The functional group is CONH2, and that is acetamide group. And we need to identify the hybridization. So with this C is connected with this four kind of legged carbon, so that is sp3 hybridization. And when we talk about bond angle is 109.5 degree. And with this C, it is connected with 1, 2 and 3 entity, so which is sp2 hybridization. If it is sp2, it's diagonal planar, 120 degree. And nh2, so that is 1, 2, 3, 4, it's 4 entities, so n is sp3 hybridized is 109.5 degree. So that is hybridization and bond angle. Identify pi and sigma bond. So basically CH is sigma bond, C double bond O, sigma and pi bond, it's 1 sigma 1 pi bond. And then NH is sigma bond, so that you can identify. Orbital picture overlapping those, so we need to draw orbital picture showing overlapping of orbitals. So let's see how we can do. I need more space here. See if I can scroll. Okay, I do have some space here, so I'm gonna scroll here and let's see if I can draw. So basically CH3, so this is with H, and then this C and this C overlap and make sigma bond. This C and this N overlap and make sigma bond. This is making H bond. This is making H bond, and this is 2 dots here. Now when we talk about oxygen, so I'm gonna let me take this electronegative color. This is oxygen, and which has about 2 electron pairs, I would say 1, 2, 3, 4, 5. So it has a kind of 1, 2, 3, 4, and you can see, and that is, let me see if I can draw it correctly. And on carbon, on this carbon there is, oh, I need blue color one. This is carbon. Okay, so these pi electrons when you look at, and this is pi electron on oxygen, when they overlap makes the pi bond. So that is something you can draw in orbital diagram, orbital picture. So pi electrons basically overlap on oxygen and carbon, and that's how we make the pi bond. This is sigma bond and this is pi bond, one pi bond. Now when we talk about formal charge, so we need to have this formula: valence electron minus number of bonding electrons minus 1/2 bonding electrons. Okay, so we have CH3. When we plug for the carbon in CH3, carbon has 0 formal charge when you calculate according to this formula. C double bond O, carbon has 0 formal charge. In C double bond O, oxygen has 0 formal charge. Again, you can calculate in NH2. Nitrogen has 0 formal charge. So again, you need to plug and chug in that formula. So how do we draw resonance? So when we draw, I'm going to erase this area so I can draw the resonance. Okay, so now we need to draw a resonance. So let's say, how do we draw the resonance? Here I'm going to draw the resonance. For C double bond O, NH2, CH2, and has 2 dots here. And remember, this nitrogen has a lone pair of electron which is going to pull up by this electrons, and that carbon is going to go here, electrons. So electrons are shifting, and due to that it forms resonance. So in that one you see NH2 becomes plus charge and is losing 2 electrons. It's moving towards oxygen. And then oxygen has 6 electron pairs instead of 4. Okay, so it is a negative charge, and then CH3. So you can see there are 2 resonance forms in here. All right. So resonance structure of acetamide, it's right here. All right. Now let's go look at another example. Degree of unsaturation for CH3, C3H6O. So when we draw its structure, H3C, C double bond O, CH3, you can say that it has a degree of unsaturation is 1. Degree of unsaturation is 1 for this compound. And okay, so you can see double bond oxygen, the oxygen in the compound is saturated or a ring. All right, now we need to draw its constitutional isomer. So I'm trying to draw that. H2C double bond CH, C OH, H and H. You can see the formula is C3H6O. The another one is C double bond O, H, and you can see, and then the other structure, which is H, there are two H's here, so total 4, we need 6, so there is a 6 hydrogen and then oxygen here. So there are 3 constitutional isomers for this compound. These are 3 total. Alright, so which one do you predict would have the highest boiling point and why? Alright, so when you look at the one that has OH, that will give the highest boiling point. So I'm going to draw that here. So when you have H, C, OH, H, so that basically gives OH, basically makes the hydrogen bond, and that is basically I would say that's why it has a highest boiling point, because it's a one molecule to other molecule. This is going to join with other molecule, and that's something, it's intermolecular forces. All right, which one would be the most soluble in water? So we know that CH3 2 C double bond O, this is acetone. It can form hydrogen bond with water, and when they form hydrogen bond, they form dipole-dipole interaction, and that's why they are soluble. It's a dipole-dipole interaction, and that's why they are soluble. Now let's look at the compound. We have given 2 chair position, and we need to circle the most chair conformation. So we have larger group at equatorial position. This is at equatorial position, large group at equatorial position. Equatorial position, and this is a small group, that is axial position. At axial position. Now when you look at this one, large group, it is axial, and smaller group equatorial. Smaller group equatorial. So when you compare, usually the larger group at equatorial, it is more kind of stable. So in this one, the large group is more stable because at equatorial position. That's why this is more stable. All right. Remember, stable, least energy, and high potential energy, stored energy. So when we look at these 2 energy diagram, and you can see this one has higher potential energy. Now draw E and Z stereoisomer of 3-methyl 2-pentyl. So let's say, so this is 3-methyl 2-pentene. Okay, so this is the one. I'm gonna draw this structure in a side. Okay, CH3, and then we will draw E and Z configuration. So this is basically, this is 3-methyl 2-pentene. Okay, so when we draw, it's a Z position, so we can say here and that is a Z 3-methyl 2-pentene. And for trans, so let's see how do we draw the trans one. Trans is more stable, and that basically I need more space here. So let's see, I'm gonna try here. CH3, CH2, CH3, CH3. So that is trans. Trans usually more stable than cis because those are at opposite sides, and so that's where the repulsion among its group and atoms compared to be less, and I mean they are equalized, so they are more stable compared to cis one. There is an interaction happens. All right, now let's see the next example. I'm going to scroll up. We need to draw 1-butene, cis-2-butene, and trans-2-butene. So, okay, 1-butene. So it's CH3, CH3, hold on. H3, CH2, CH, double bond CH2, that's 1-butene. Then we have a cis-2-butene. We have cis-2-butene. This is a cis position, both CH3 on the same side. So this is cis-2-butene. Okay, and then trans. So we have CH3 here, CH3 here, so 4-carbon chain and with a double bond, so that's why it's a 2-butene, but this is trans 2-butene. All right. Now, what kind of isomers? And 1-butene and cis-2-butene. So, when you look at, they are geometrical isomers, right? So, they are geometrical isomers. All right. Rank all three in terms of stability. So, when you look at, trans is more stable than cis, and then so when you draw the structure, I'm trying to draw the structure here. C double bond C, CH3, and this is a trans. This is a trans, as you can see they are distributed, so this is more stable than cis structure. This is a cis structure, and then it's a butene. So when I draw the structure, you will see 1 2 3 4. Okay, and this is one butene, is that right? And then you consider H around, so basically you can say that trans 2-butene has greater stability than cis, and then 1-butene. All right. Write a reaction equation for hydrogenation of 1-butene. All right. So hydrogenation of 1-butene. Reaction equation. So in this one, okay, you know what? I'm going to move this thing here. All right. So when you look at here, 1-butene, is less than cis 2-butene, and then trans 2-butene. All right. You know, this one we'll discuss later in the next video, or you can definitely pause this and identify hydrogenation of 1-butene, so that way I do not have enough space. All right. Hydrogenation of 1-butene, cis 2-butene, and trans, all are exergonic reaction, yield same product but release different amounts of energy. Draw the energy diagrams. I'm trying to draw that. So E, or you can say delta H, is 0, and when you look at it is producing around a negative 27.6 kilocalorie per mole. Cis, basically it produces negative 28.6 kilocalorie per mole. This one is negative 30.3 kilocalorie per mole. All right. So trans 2-butene is this is the most stable. This is stable, and so basically it has a lower heat of hydrogenation. So when you look at its activation energy and reaction, and you can see the activation energy. So when you look at the more stable, EA1, and this is EA2, and you can see activation energy of catalyzed and uncatalyzed reaction, and it's a lower heat of hydrogenation. This one has stable, trans is stable, It's a lower heat of hydrogenation. All right. So basically, um, so here we finish few examples. I would highly suggest some of those reactions. You need to find it. They're in a textbook and work on it. And again, though these examples, you need to work on it, and then you can, whenever I go over this video, you need to check your answers and make sure you are doing it correct. All right.